Two things to note. The assignment I talked about yesterday, the additional assignment, should show up in about 5 minutes as available. It is a 2-point quiz. It is basically another reflection question. You're going to look at your exam. You're going to look at that last question that I asked you about and respond to that again. Please take the time. It's not due until Sunday. You have plenty of time. No urgency to that at all. The second thing is a typo on the homework list. I did upload a corrected version to our Canvas page. Bonus question there in that homework is problem number 66, not problem number 60. But that's for tomorrow's question and answer session. Today, I want to do another derivative rule. The chain rule. One of the exam questions had the function y equals 1 over 2x to the 5th. And I asked you to find the derivative of this. A number of people rewrote this with a negative exponent. You've got stuff in the bottom, so you want to take it out of the bottom. I like this. This is a good idea. Problem is, those people who took stuff out of the bottom, a lot of them wrote that. You're shaking your head at me. What's the problem with what's written here? Bethany, tell me what the problem is. That's okay, though. This can go to a -6 power. That is correct. But the problem, the 2. There's no power on the 2. The 2 should not have gone up here. The 2 actually stays in the denominator. Then you can do the power rule perfectly fine. If I want to think of bringing the 2 out of the bottom, I have to think about bringing the whole thing out of the bottom. And then I could think of taking this entire thing out of the bottom. But if I bring it out as one whole thing, then it's just one thing. And it gets raised to the -1 power. And now my brain goes, whoa, I don't know what to do with that. I could apply my rules for exponents. When you have a power of a power, what do you do with those? I multiply them together. But that only works for the x. The 2 would also have to get that -1 power. What power is that 2 raised to right there? Inside. The first, which means I would end up with 2 to the -1, x to the -5. Oh, okay, but 2 to the -1 is the same as 1/2. This is the same thing. It works. I'm okay with that. But as soon as I see something like this, I start to think of myself, wait a minute. Ugly stuff to a power. What if I just thought of that as a different thing? U for ugly. Problem is, when I do this, if I try and use the power rule here, I don't have the right power rule. So my power rule derivative says take the derivative with respect to a variable. And the variable in this problem is x, not u. String of profanity running through my head. Dang it. When I think of switching that from 2x to the fifth all to a power to just being a single variable, I'm really thinking about one function inside another. Function inside another. We had a name for this back in the algebra class. Put the output of one function into another function. What did we call that? A composite function. So I want to think about doing this like composites. I think of an f of g of x. There's a function on the outside, my f of x. But instead of just having x inside, I've got a whole other function inside. If I just think of the outside function, I can take the derivative there. But that's not the right derivative, because I still have this. So now, you need to think about this derivative as a two-step process. If I measured the change out here, that would be my derivative like it was just the u part, right? What's the derivative of u to the minus 1 in terms of u? Pretend that's your x. What is the derivative of u to the minus 1? Minus 1 u to the minus 2. Perfect. Problem. That ignored my inside part. That only dealt with the negative 1. But it's not just the x to the negative 1. It's not just u to the minus 1. That u is something else, right? So let's think about the u part as if it was another function. I can think of the derivative with respect to x of that part. Wait a minute. I know how to do this. What's that derivative? That's nice and easy. But I've written this like this. And that thing on the inside, that's u, right? So this is du dx. But this part, that's the outside function, isn't it? That's the outside. If that's the outside, that's f. That means that this is really df du. But this sentence back up here, I don't want to take my derivative with respect to u. I want to take my derivative with respect to x. So the thing I want is df dx. And the pieces I have are df du and du dx. Hang on a minute. Fractions. If I take df du and I multiply by du dx, what happens to my du's? Holy crap, that works. Except df du up there is written in u, right? I want to finish with everything in X. So here's my cheat. Instead of writing the letter U here, I'm going to write the stuff that U is in terms of X. Minus 1 U to the minus 2, but U is equal to 2X to the fifth. So this is going to become minus 1, 2X to the fifth to the minus 2. That's the df du part. Du dx, we already did. That's right here. It's 10x to the fourth. If I multiply these together, this is to a negative power. Where does stuff with negative powers go? Down. There's a minus sign. And there's a 10x to the fourth. Let's play the power game again. What do I do with this squared on the outside in the denominator? I'm going to distribute it in. What's 2 squared? And x to the fifth squared. Ten divided by 4 can be simplified. What do I get when I simplify it? 5/2. X to the fourth on top, x to the 10th on the bottom. What do I do with the powers of x? 4 minus 10. And that is the right answer to that part of the problem. I got this negative times this 10. Holy crap. If I put together this idea of inside and outside, I take the derivative of the outside, leaving the inside part all alone. And then I take the derivative of the inside and multiply it on. I get the right answer. Now, some of you are looking at me like I'm a space alien at the moment. So let's try this a different way. Here is a nice function. G of x is x squared. You know the derivative of that, right? There should be a chorus. I see 2 voices. Come on. 2x is the derivative of that. I'm going to do x squared cubed. The inside part is the x squared. The outside part is thing cubed. This is f of g of x, because the g of x is on the inside, right? So wait a minute. If that's the case, then if I were to write f of u, what is the formula for f of u? F of thingy was thingy cubed. So f of thingy is thingy cubed. F of ugly junk is ugly junk cubed. I'm perfectly fine using ugly junk as a variable. I don't care what variable you use. It's a placeholder. And I'm very happy to say f of u to this problem. I made that up. That's in the problem I've got right here. Now here's the fun part. I have a power of a power. X squared cubed is the same as what power of x? Multiply the powers together, right? So what's the derivative of that? Keep that in your back pocket for the moment. What is the derivative of ugly stuff cubed? with respect to u, with respect to the ugly stuff, it's 3 ugly squared. So f prime of u is 3 ugly squared. I'm going to take the derivative of the outside. That's what we just did. I'm going to leave the inside alone. Instead of u, I'm going to write x squared. But wait, there's more. Notice x squared squared is the same as what power of x? It's the 4th power. I'm off by 1x. I'm also off exactly by a factor of 2, aren't I? Exactly what is needed is the extra derivative from the inside. Now, I'm the first to admit that if I saw x squared cubed, I would undoubtedly do it this way. Because power of power is easy, right? Here's your next thing to take the derivative of. Take the derivative of x squared plus 1 to the 100th power. Not just no, hell no, I'm not multiplying that out. You imagine expanding that binomial 100 power? No. Even with Pascal's triangle, that's going to suck. I don't want to do it. But it's ugly stuff to a power. It's a composite function. There's an inside and an outside. What is the outside function? We'll write it in a different letter. If you don't like using u, feel free to use any variable you want. F of weird face. I don't care what variable you're using. F of u is u to the 100th. But then the inside is the x squared plus 1. So if I want to take this derivative, I'm going to take the derivative of the outside with whatever variable is there. So what is f prime of u? (100u to the 99). I'm going to put this back in it. So the derivative I am after is 100 ugly to the 99, but wait, there's more. Infomercial voice. Order today and you will get, for no additional cost, the derivative of the inside. What's our derivative? I want you to imagine for a moment that you spent an hour working out x squared plus 1 to the 100th power. Then you took the derivative, and then we factored it. People, I would rather hit myself in the head with a 2x4 until I passed out. This took less than a minute. All because I can figure out how a composition is written as an outside and an inside. I will say write it this way in general. We were talking about a composition as f of g of x, right? I'm thinking of taking the derivative of this. I'm going to take the derivative of the outside, f prime, and I'm going to leave the inside all alone. Prime's now just on the f. Don't touch g yet. Then do the derivative of the inside as an extra bit multiplied on. Well, yeah, because that means I'm only taking the derivative of the f part. That's why on the left-hand side, it's outside the set of parentheses. Because where would I put it otherwise? And that's partially why I like the ddx notation, because it's clear from this way of writing it that the derivative is applying to this whole thing. If I just float it up there somewhere, what does it apply to? Well, here it's only applying to f, and I'm putting the argument, the thing that goes in, is g, as opposed to just being the variable x. And then here, on the end, I'm taking the derivative of g, and the thing that goes in, the argument, is x. Once again, I'm going to show my age. Dr. Seuss books. The Sneetches on the beaches. I see a couple of heads nodding. The rest of you should Google this. Two machines. You come out of one and go into the other. I come out of one function, I go into the other. Extra things get spit out when I look at the changes. This now allows me to take the derivative of all sorts of weird things. Straight to that. Percy. Thank you. Evan. Yes, that is a 1 at the end. It's inside the root. I'll put a little tail on my roots, you know where it ends. What do I do with square roots? I put everything to the exponent of 1/2. Notice I said take the derivative of, and the 1/2 is inside those derivative of parentheses. Inside versus outside. The inside part is everything inside that set of parentheses. And the outside part's the 1/2 power. So it's thing to the 1/2. So the derivative is, well, derivative of a 1/2 power is 1/2 junk to the negative 1/2. And the junk doesn't change. Gesundheit. But wait, there's more. What goes there? The derivative of the junk. The derivative of all of this. As you saw on the exam, I am a firm believer in not simplifying. Leave it like this, you're perfectly fine. But if you're asked to do something with this, like one of the questions in the homework says, find the tangent line when x is 0, then you got to plug in 0. I can plug in when it looks like this. One of the other questions in the homework said, find out where it's equal to 0. If I want to set that equal to 0, I need to do the algebra to simplify it. So it depends on what you're doing with your derivative as to whether or not you're going to simplify. Negative powers belong, Gesundheit, in the bottom. So I will have a square root because it's a 1/2 power in the bottom because it's negative. 1/2 means that there's going to be a 2 on the bottom. This stuff doesn't have any negative powers on it. It stays on the top. Ta-da! As long as I can be sure of which part is the outside. Here's one side again. It's the right time. We're all getting rained on. It's time for sneezing. As long as I can be sure of what's the outside, what's the inside, which piece I need to differentiate at what point in time, this works. Questions? I got about 8 more examples. I'll get there. See, that's the best part, is I have an outside and I have an inside. All you have to be able to do is write what pieces. You'll notice I didn't write what U was. I didn't write what outside versus inside. I just did the derivative in two parts. Other questions? What is the derivative of sine of x squared? The outside part is the sine, right? And the derivative of sine is cosine. So it'll be cosine of junk, and junk doesn't change. Insert announcer voice here. But wait, there's more. What goes on the end? The derivative of the junk. Now, here's where I will make a guaranteed statement. I don't like this. Having the x squared and the 2x both on the end, they both look like they kind of belong to the cosine. Especially because I see a lot of people not write parentheses around stuff with cosines and sines. I will almost always put the derivative of the inside part out front when I'm dealing with trig functions, for precisely that reason. This is, of course, completely optional. When you use all the parentheses, then you'll get this absolutely right. I'm going to tweak this problem just a little. How is this function different from the one we just did? Say that louder. It's sine squared, not x squared, which means the outside and the inside switched roles. The sine is what's being squared. That means the outside part is the square. Because really, this notation is short for that. Again, twitch, twitch, twitch. Sine squared. Sine squared of what? Sine squared of whatever you put there. But the sine is the square that makes the sine the inside and the square the outside. And that means that the derivative of thing squared is 2 thing. But wait. Derivative of sine. And again, if I'm really being anal retentive, all of these arguments should have parentheses. How much of a tight ass do you want to be today? As long as I can tell inside from outside, I'm good to go. Questions? What do you mean? Fraction in what way?
The outside.
You mean something like this or something the other way around? Well, we'll do one the other way around in just a minute. Yes, sir. This one, that's just over here now. I just put it out front. It's just being multiplied to a different place. Like there's a dot here. It's cosine of x squared times 2x. Do you want to put the 2x on the end, or do you want to write it 2x times the cosine of x squared? When you're multiplying, a times b is the same as b times a, right? So that's all I did is I reversed the order in that set. It's completely an optional step. If you don't like it, leave it like this. That's perfectly correct. But the x squared is attached to the cosine and the 2x isn't. So I want to put it in front of the cosine rather than behind it. Personal peccadillo of mine. I'm sorry? Oh, yeah, there are lots of rules here now. But again, now I have some choice. I have some room to play with this problem. You have at least 3 different ways of doing this problem. At least. I could say this is ugly junk to the 9, right? If I do this as ugly junk to the 9, what's the derivative of ugly to the 9? 9 ugly to the 8. So I could start by saying this is 9 junk to the 8. But wait, there's more. What goes inside that set of parentheses? My quotient rule goes inside those parentheses. Bleh. All right. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. Bleh. Method number 1. Trinity, you just look like I hit you in the head with a fish. Talk to me. Oh, yes, my handwriting sucks. 2t minus 2. I was jamming up against the edge there and started to run out of room in my parentheses. That's method 1. But another thing I could say is this is a fraction to a power. I can do algebra first. And I can say instead of making that ugly to the 9, I can make a thing to the 9 over thing to the 9. Because this power can be distributed. And now, the outside part is the quotient. Look at what you would do if you plug in a number. If you plug in a number, you take the number, subtract 2, raised to the 9th power. You take the number, multiply by 2, add 1, raised to the 9th power. And then last, you would divide. Which means the rule I'm doing on the outside is the division. The first thing I need to do is the quotient rule. But when I take the derivative of the top, there's a chain rule. And when I take the derivative of the bottom, there's a chain rule. So this actually has 2 chain rules inside a quotient if I do it this way. Derivative of the top, 9 ugly junk to the 8th times the derivative of the inside. What's the derivative of the inside? Just 1. Derivative of the top times the bottom minus derivative of the bottom, 9 ugly junk to the 8th times the derivative of the inside. What's the derivative of the inside this time? 2. Derivative of the bottom times the top, t minus 2 to the 9th. All over the bottom squared. Those algebraically are the same thing. I don't know about you, but I like the top one a little bit better than the bottom one. But maybe you're like me. And maybe the quotient rule is something that makes you go barf. I hate the quotient rule with the white hot passion of 1,000 suns. I did promise you, though, I would show you where the minus sign came from in the quotient rule. Ready? I have a quotient here. I don't want to do the quotient rule. The quotient rule sucks. So I'm going to change this from a quotient to a product. By taking that thing out of the bottom to the -1 power. And now when I do the derivative, I've got a product, and the second piece has a chain in it. Product rule. Product rule says take the derivative of the first part. Leave the second part alone. Then leave the first part alone and do the derivative of the second. Ugly to the -1. -1, ugly to the -2. But wait, there's more. Derivative of the inside. Hey, there's a subtraction right there. I'm about to do a little messy algebra. This piece is to a -2 power. It goes in the bottom. What's left on the top of that fraction? There's also this x squared, isn't there? There's the x squared from here, and there's the 3x squared from here. I'm going to leave them separate for the moment. Look at the other one. The other one is 2x over x cubed plus 1. If I want to subtract these two fractions, I need a common denominator. The left fraction has a denominator of x cubed plus 1. The right fraction has the same thing but squared. So I would need to multiply the left fraction by 1. But that 1 would be x cubed plus 1 on top and x cubed plus 1 on the bottom. X cubed plus 1 on the top and another 1 on the bottom. And now when I put these together, let's read it across the top. Derivative of the top times the bottom minus derivative of the bottom times the top over the bottom squared. The quotient rule comes from the product rule and the chain rule and a common denominator. You never have to do the quotient rule again if you don't want to. I promise I didn't pull it out of my ass. Where'd the bottom squared come? Right here. Common denominator. That's where it came from. Questions? Yes, ma'am.
For the 3x squared that you tagged on the end, yeah, right there. Why did we do that?
That's the chain rule for this part. -1, this is the outside part. That's the inside part. Oh, the problem above? What I would do is I would rewrite that bottom part, 2t plus 1 to the 9th, as 2t plus 1 to the -9th. And then it would be the product rule instead. I don't have to do the quotient rule. Yes, Blake? Oh, sure, I could leave the answer like this. I just wanted to show you that the algebra actually leads me to the quotient rule. Unless I'm going to do something with it, don't simplify. More questions? What's the derivative of e to the x? E to the x. So if that's the derivative of e to the x, what's the derivative of e to the 2x? Where'd the extra 2 come from? This is the outside function is the exponential. The inside is the 2x. I read it over there as e to the x. That's putting the x on the inside. This is e to the 2x. The 2x is on the inside. And yes, here's another case, Patrick, just like the other one. I want to put that 2 out front because I have bad handwriting and I can't always tell what's up and what's down, especially with no lines on the paper. So I will almost always write that out front. Why? If I write it that way, then it'd be e to the x. But I'd first have to do the derivative of x squared, right? What's the derivative of ugly stuff squared? Gives me the same result. Because I multiplied powers here, I can think of e to the 2x as e to the x squared. If I do the chain rule, that's ugly squared. The derivative would be 2 ugly times the derivative of the inside. But then when I multiply those, I have to add the powers together, and I get exactly the same thing. Again, as long as I'm playing by the rules of algebra, I can use whichever derivative rule I like better. If I want the derivative of this nasty mother, again, it's e to the junk. The derivative of e to the junk is e to the junk and more. The derivative of e to the x is e to the x. So the derivative of e to the barf is e to the barf, and then the derivative of the barf. That's all I have to do every time. It's the chain rule. I get the same thing back. And then I get more, which in this case, I'm going to put out front because I don't like having no lines and not being able to tell what's up versus what's down. I will freely admit, as a math person, I love using e to the x. It's the only exponential I really want to use. But as a science person, as a defrocked physics major, I did a lot of stuff with powers of 10. So what if I asked you for the derivative of the function 10 to the x? Or maybe 2 to the x, or 3 to the x, or any other number to the x. What if my base isn't e? Back before the exam, we did the derivative of e to the x, and we used this limit idea, right? I don't want to do that here. But I could use the exact same setup, and I would have this extra term involved. I don't think it's worth going back to the limit definition if I can figure out how to change the base in an exponential. We had a formula for this. But rather than remember any formula, E and ln undo each other, right? So I'm just going to think of this 10 here in the middle. And I'm going to say, you know what I can do? Is I can say 10 is the same as doing an E and an ln to 10. This is the same as an E and an ln to 10. Because they undo each other. Now, I don't know about you, but I don't have ln of 10 memorized. But I do know that ln of 10 is a number. Somebody who's got a calculator out, what's ln of 10? 2.302 ... keeps going nauseatingly forever, right? But it's a number. Just remember the fact that it's a number. Just like 2. I can write 10 to the x as this to the x. But I now have a power of a power, which means I multiply my powers together. So this becomes e to the ln 10 times x, just like it was e to the 2x, or e to the 5x, or e to the 73x. What's the derivative of e to the number x? The derivative of e to the 2x was e to the 2x. But wait, there's more. So the derivative here is e to the number x, but wait, there's more. In the previous example that is just scrolled off the top of my paper, what went inside the parentheses when I did e to the 2x? What was that, Jordan? Just the 2. So in this case, the number, the derivative of number x is number. The derivative of 2x is 2. The derivative of 3x is 3. The derivative of 73x is 73. The derivative of ln 10x is ln 10. The derivative of 10 to the x is 10 to the x times the ln of 10. There's my change of base piece. If this base is anything other than e, I get that ln outside. What is ln of e? They cancel each other out. I just get 1. Which is why e to the x's derivative is e to the x times 1. I don't care what base you're using. As long as the base is a positive number other than 1, this works. I believe this is in the textbook on page 204. Although they might use 2 to the x instead of 10 to the x. Same process. 2 to the x shows up an awful lot in computer science. We're doing everything in powers of 2 instead of powers of 10. All the chemists, all the physicists, they work in powers of 10. Math geeks like me work in E. Just multiply by a constant, it fixes it. Questions? Let's apply. Here's a function, f of x equals sine 2x minus 2 sine x. What x values for this function have a horizontal tangent line? What is the slope of a horizontal line? 0. If the slope is 0, and I want to know where the tangent line has a slope of 0, I want to know where my derivative is 0. So this question is really equivalent to asking, where is my derivative 0? But you know how to take the derivative of this. What is f prime of x in this case? The derivative of sine is cosine. Here it's cosine of junk with a 2. That's the chain rule. Derivative of sine is cosine. So really, I want to know 2 cosine 2x minus 2 cosine x equals 0. I'm sorry? Nope. I want to know globally, because this happens infinitely many times. Trig functions wiggle back and forth forever. So I better come up with an infinite collection of answers. Hold that thought. Hold that thought. I promise I'll get there. The first problem is, how the hell do I solve this? For those of you that took trig here with either Mr. Nichols or Dr. McNabb, chapter 7, section 3, 7.4, solving trig equations. We did this. If you don't remember it, go find your trig book. Go over to the enrichment center and bury yourself in one of their trig books. How the hell do I solve this? My problem is the fact that those have different arguments. The first one is cosine of 2x. The second one is cosine of x. Lindsay, you've got your textbook, yes? Flip to the back where those trig things were in the appendix. Appendix D for all the trig formulas. I need the trig formulas. If you don't have your book with you, if you got your computer, go to the Canvas page. Let's take a look at the trig formula sheet that's there. I need a formula for cosine of 2x. There are several of them. I think, Evan, when you were talking about it was like age 829 or something like that in the back book. So we're in that range. Somewhere in there, there's a cosine of 2x formula. Well, if I did cosine squared minus sine squared, I'd have cosines and sines in this problem. Lindsay, do you have one that's just cosines? Aha. So I can replace this with 2 cosine squared x minus 1. And then everything's in cosine of just x. This makes me much happier. If I'm going to work in trig functions, I want the trig function part to be as simple as possible. That gives me 4 cosine squared x minus 2 cosine x equals 0. I'm going to divide by 2. Everything's got a multiple of 2 in front of it. I'm going to divide by 2. Oh, hang on a second. Cosine squared, cosine number. This is a quadratic. Thing squared, thing number. As a matter of fact, let's rewrite it in the right order. 2 cosine squared x minus cosine x minus 1. That's a quadratic. 2u squared minus u minus 1. Or 2f squared. I don't care what variable you want to use. Just don't use x again. That's a quadratic. If you want, you can use quadratic formula. Or you could factor this. All right, wait a minute. I've got 2 ugly squared minus ugly minus 1 equals 0. I've got a 2 here. That means I'm going to need a 2 and a 1. I've got a 1 here. I'm going to need a 1 and a 1. Normally I would write u, but I'll write cosine of x instead. One of those gets a plus, one of those gets a minus because it's a negative 1. Which one is negative? Which one is positive? I want these two to multiply to give me minus 1. One has to be plus, one has to be net minus. I want them to add. I need to subtract these to get a negative. I need negative 2 and positive 1. Plus here, minus there. If you are looking at me like I have just done something that you have never in your entire adult life seen, use the quadratic formula. That's fine. You'll get exactly the same answer. You'll get from here 2 cosine x plus 1 equals 0. So cosine of x is minus 1/2. You'd get u equals minus 1/2. Here, cosine of x minus 1 equals 0. So cosine of x is 1. And now I need to know my unit circle really damn well. What values of x have cosine equal to 1? 0. And every time I go around the circle, every multiple of 2 pi. So I end up with x equals 0 plus any multiple, positive or negative, of 2 pi. That's cosine x equals 1. Cosine is negative. In which 2 quadrants? 2 and 3. Cosine is 1/2. For what angle? Mumble, mumble, murmur, murmur. See, this is why you need your unit circle. If you do not have your unit circle memorized, please flip back to Appendix D. Let's start pulling stuff out. You can go get a unit circle at the Enrichment Center, fill it in, tape it to the wall, and stare at it until it's embedded itself in your brain. 1/2. Cosine starts here and goes down. 0/2, 1/2. Which angle is that? I don't like degrees. Degrees are evil. I want radians. That's pi/3, 60 degrees. But I'm in the second quadrant. That's 2 pi/3, 120 degrees. I'm in the third quadrant. 4 pi/3. Plus any multiple of 2 pi. Because I can keep going around the circle as often as you want. Like I said, if I'm just taking a derivative, I don't care what I'm going to do with it. I'm not going to simplify anything. But if I need to do something with it, I may have a lot of algebra in front of me, especially things involving trig functions. I'm going to end up doing this a lot. We're going to see over and over the need to find a derivative and do something with it is a huge part of this class. Questions? Some of my favorite functions are composite functions. This function, 1 over the quantity 1 plus ae to the minus kt. A and k are just numbers. This happens to be a very useful function. The graph of this function has two really nice properties. I would like to look at the asymptotes, the limits, as we go to minus infinity and as we go to infinity. So let me think about this for a minute. The limit as t goes to infinity of this function, as t gets bigger and bigger and bigger, what happens to this power? Gets more and more negative. E to a negative is very, very small, right? So as e to the negative gets small, number times e to the negative gets small. As we go off to positive infinity, this gets tiny, which means this limit is 1. On the other hand, if t is negative, then e to the negative times negative, that's e to a positive. E to a positive is really, really big, which makes the bottom of this fraction really big. 1 over something really huge is really, really small. So this graph is 0 way out to the left and 1 way out to the right. This graph looks like an elongated S-curve. It's called a logistic function. And it has to do with growth in restricted environments. If I give you, we've done this one before. Here's a colony of bacteria. An hour later, there's twice as many. An hour later than that, there's twice as many again. We get an exponential function, but that's unrestricted growth. Eventually, I will have enough bacteria that they will be the only living thing left in the world. That's a bad idea. My bacteria are growing in a little petri dish. I've been in the micro lab. It's only about that big. There's a limit to how many bacteria I can have in a dish that's 4 inches across. That limitation on space acts as an asymptote. Eventually, I will have taken up 100% of the space in my growth medium. If I have a rumor about something, eventually it will have been heard by 100% of the people, right? This represents a really good model of a limited, restrained growth. Figuring out what this asymptote is for various values of A and K, where the bend is, where are we growing fastest, I can take the derivative of this thing and figure out my growth rate. And then I look at how that growth rate changes. That would be a second derivative. Verhulst, I always screw his name up. Verhulst in 1876 was researching population growth and came up with this result out of looking at what I want to know about derivatives that gives me this equation. And he used this not just as a model for population growth, but for information spread, for skill development. The longer you work at something, the best way to learn how to do something is to suck at it. The first time you learned how to walk, Did you just immediately go out and do a marathon? Hell no, you fell over and bumped your nose. You have to suck at it for a very long time before you start to get skill and get better and get better and get better until you reach a threshold of proficiency. At some point, you're as good as you're going to get at whatever skill it is. Being good at something means being willing to spend time here. I will never be an Olympic fencer. Trust me, my fencing skill is still down here because I don't spend the time struggling in it. I don't spend the time uncomfortable in it, sucking at it. The longer I spend sucking at it, the better I'll get. Maybe really slowly, but eventually that'll turn up and then I'll get good. That's how I've been doing calculus for 40 years. You've been doing it for 4 weeks. It's a difference, right? You were starting to ask me a question. Okay. I should be able to take the derivative of this thing. I sure as hell don't want to do the quotient rule. So I won't. I'll take this entire expression and rewrite it as 1 plus a e to the negative kt to the minus 1. Which means when I go to do the derivative, I need the chain rule. I need the chain rule twice. Why do I need the chain rule twice? This whole thing is raised to a minus. So I'm going to do the chain rule for the outside there. But that's exactly right. There's another exponent that's a double in here, isn't it? So when I do this, I'm going to go, okay, P prime is minus 1 ugly junk to the minus 2. But now I need to do the derivative of the inside. And the derivative of 1 is, there was supposed to be a chorus. Don't leave me hanging, people. What's the derivative of 1? 0. But that means a e to the kt. The a is a constant multiple. It stays there. What's the derivative of e to the junk? It's not just a t. I need to do the chain rule again. There's another layer in my composition. The derivative of e to the stuff is e to the stuff. But wait, there's more. Order early today and we will, for extra special, give you another derivative for free. What goes here? Negative k. Number t, the derivative is number. Hey, wait a minute. I have a negative being multiplied here. I have a negative being multiplied out there. Those will cancel. I don't care how many layers you want to go. I don't exactly have the one with all the Doctor Who's in it, but it's the same idea, isn't it? How far do you want to go? It works. When I interviewed here 20 some odd years ago, they asked you to do a lecture. The lecture I did was on the chain rule. The following is the problem I ended my lecture with. Sine of, ln of, inverse tangent of, e to the, that's 4 layers, x to the, that's 5 layers, x times ln of 3x to the, that's 9 layers deep, people. It works. All I have to do is keep peeling the layers of the onion back. Every time I see another inside, that's what I'm going to do. I'm going to change my frame. I'm going to pull out the next doll. Unfortunately for me, this set is only this deep. Tomorrow. Tomorrow is question and answer. If you look on our Canvas page as of right now, you should be able to see the additional quote unquote quiz that is the exam reflection. Please take the time to read the instructions and read that exam reflection carefully. Unfortunately, tomorrow's office hours are canceled because immediately after class, I'm leaving for a career fair out in Moon Township. I will send an email reminding you all of that. I will see you all tomorrow. Have a wonderful rest of your day. Yes. Here. Okay, the derivative of 1 is 0. The derivative of number e to the number. The number is being multiplied, so it stays there. The derivative of e to the stuff is e to the stuff times the derivative of the stuff. E to the 2x gave me e to the 2x with a 2. That's our chain rule. Because really, e to the number x, e to the minus kt is the exponential of minus kt. You see how it's on the inside? So when I do the chain rule, I got to have the extra derivative of the inside. So the derivative is e to the thing again. But wait, there's more. The derivative of the inside. What's the derivative of number x? It's just number. So let's actually do numbers. E to the minus 3x. The derivative is e to the minus 3x again times minus 3.
But I actually see that.
Of the outside, leave the inside alone, and then multiply on extra the derivative of the inside. Well, in this case, I think of e to the stuff as e of stuff. It's the exponential function of something. I like it when it's tangent or sine because then I've got of parentheses, right? Or stuff to a power because I've got parentheses. E, because it's written like this, if I write it like that, it makes a little more sense. Does that help? Yay. All right. Let me stop the recording.